That ends chapter 6 in your text. The book does go over probability generating functions, but it's a bit involved, so I'm not going to do that here. Move on to 7, which is on joint distributions. Any thoughts as to what a joint distribution is? Distribution of two distributions. Very close. It's not two distributions. It's distribution of two random variables. So So if x and y are two random variables with their own PMFs, x is equal to n and y is equal to n, then the joint distribution of x and y is probability of x is equal to n, comma, y equals n. This is what we call the joint distribution. Probability of x is equal to n and probability of y is equal to n. They are just PMFs, but we also call them as marginal PMFs or marginal distributions. So right. So we have a joint distribution. We have marginal distributions. So now we have to find a conditional distribution. How do we go from here to a conditional distribution? Okay.
Would it be the finding y is equal to n given x is equal to something else?
Yeah. So let's just say I want to find probability of x is equal to n given y equals n. Right? Now, what would that conditional distribution be?
Probably
What?
is there two discrete variables?
I did not say that they are independent. They're just two random variables. So unless otherwise specified, random variables are not assumed to be independent. So given y equals n would simply be probability of x is equal to n, y equals n, divided by probability y equals n. If they are independent, then this is correct. It will simply be equal to x is equal to n. But we don't even need math to come to that conclusion, right? Bit of common sense. If x has nothing to do with y, that doesn't matter. right? It'll just be probability of x is equal to n. Just by looking at this expression, it should remind you of something. This should remind you of something. I'll give you a hint from right. Right, this is the definition of conditional probability, right? I'm just extending it to multiple variables. That by definition is what a distribution is. If you look at just one event, you have the probability of that one event. But if you have a bunch of outcomes, and if you summarize the probabilities for all of those outcomes, then you have a distribution. So if I vary m, whatever support that might be, if I vary m for a particular fixed value of y, then I will get the conditional distribution for x given that specific y. And if y has its own support, for each different value, you would end up having a whole bunch of conditional distributions. Does that make sense? Okay. Let's say if you remember contingency tables. Statistics 2023.
Is this the true and false?
Close. It's not coming to me. Let's see. Give me a scenario where two things could be related. Make this interesting. So we'll say we'll call this y, we'll call that x. And contingency tables are quite useful in social sciences, psychology, and fields of that sort, where we have qualitative responses like this. So the chances of singing karaoke measured low, medium, high, and the number of beers that you have 0 to 5, 6 to 10, 11 to 15. Those are the probabilities. We have two random variables, and if I want to find the BMFs of x and y just by themselves without bringing them together, what would the possible values for y be? Huh? Low, medium, and high, right?
Some horizontally back together.
Come again?
Is it like a distribution of like each row some?
Yeah, we have to make a change. I'll just wait until I do this. So low, medium, high, I'll just call it M. So if you add those probabilities, you're going to get the values, right? But there is an issue here. When I add the low, the medium, and the high, what would the sum of those be? 1.
Each row is one, each column.
Yep.
What?
Each row adds to one, each column adds to one.
Right, each row adds to 1, each column adds to 1. And there is a huge problem with this. Huh?
You add everything together, you get 3.
When I add everything together, I get 3, right? Is that reasonable? No, why not?
Because we don't like
It's only between 0 and 1.
It has to be between 0 and 1. So what should we do with each of them? Divide by 3. So if I divide, which one by 3? Just those, or the entire? Everything must be divided by 3 for us to have a proper PMF. So here I'm going to assume the probability of low, medium, high equally likely, divide by 3.
What if they weren't equally likely?
Huh?
What if they weren't equally likely?
Then we would have a different distribution, right? In this case, they are equally likely. The way I designed it, you know, sum across rows, columns, 1, 1.
So why is uniform then?
Yes, but it doesn't have to be this way. In the sense, I could have 0.5, 0.2, 0.3, right? As long as it is a PNF. I just wanted to make this problem easy. In a similar manner, I could do it for X, right? 3 possible values, and that would give us a PMF. So we end up having 2 PMFs. We call them marginal distributions because we computed them in the margin. Right. Now we want to find the joint probability or joint distribution. What would the joint distribution be?
P of X equals N, Y equals N.
P of X is equal to M and Y equals N. So 1, 1, 1, 2, or 1, 3, if you code it as 1, 2, 3. So each of them would be a joint outcome, right? What needs to happen if I add them all together? It must be 1. Now, let's go ahead and add these values and tell me what you get.
I mean, the columns that.
Exactly, we should, right?
Yeah, the columns, yeah, columns at 1 are for columns.
So it should add to 3. So what should we do? We already know that we have to divide each of them by 3. So if we divide each value by 3, we would end up having a proper joint distribution. Okay, so from here to there, a joint distribution, probability X is equal to something, Y equal to something, M and N are the possible outcomes. Two over 10. By 3. 12. 5 over 100. 1. You can verify my work. I'm just dividing each of them by 3. So 5 over 30, which is 1 over 6. That would be 1 over 12. 0.2 divided by 3, that is 2 over 30, 1 over 15. 0.65 divided by 3. How much?
13 over 16.
50.
60.
Oh, 60, 60.
It's 0.65.
It's 13 times 9.
Yeah, so it's 13/26.
Those are the actual probabilities. If you add them, it will add to 1. So this is a proper joint distribution. This is not. If you want to get a proper marginal distribution, we should divide by 3 here, divide by 3 there. And anytime when we find probabilities or conditional distributions, we're going to use actual distributions, not these. Okay, now let's say what will depend on what? Will the chances depend on the number of beers? Or the number of beers will depend on the chances should depend on that. So let's just say y equals low, given x is equal to 6 to 10. Yes. Correct. So how do we find that value?
6 to 10.
Yeah. Low 6 to 10.
Well, over 1/3.
1/12 over 1/3, which is 1/4. Yes. In a similar manner. Now, why 1/3? Because I'm conditioning on this, right? So the joint probability is right there, divided by the corresponding conditioned value or its probability, which is 1/3. Yes.
So the table to the left is showing us the conditional probability.
Is it?
So there's one for.
Well, let's test the other one too. I didn't intend for it to be, but. So once again, if y is low, I can change x to be 0 to 5. Still low, and 0 to 5, I'm conditioning on this level. So 0.6 divided by 1/3. Yes, so 6 over 10. No, over here. I'm sorry. 2 over 10 divided by 1/3. Yep. Unintended consequence, but yes. They ended up being conditional probabilities. It makes sense. And I've got one more level. Yes. What is the other level? The other level would be y equals low, given x is equal to 11 to 15. And that's probably going to equal to 0.15. So what I have here is conditional distribution. Right?
It's 1/20 over 1/3, says 3/20.
What?
It's 1/20, 5 over.
Oh, you're giving me the answer. That's 0.15.
Yeah.
Okay. So this is a conditional distribution for y being low, conditioned on all possible values of x. So how many conditional distributions would we have for y? We're going to have 3 of them. So that's what I mentioned earlier. For each possible value of y, you would end up having a distribution based on x. Good. Okay.
So can this only be
We can create a table, for example, die rolls. We could have them as 0, 1, 2, or 1, 2, 3, 1, 2, 3, and we can create a distribution for, rolling 2 dice together and finding the probability. We can do that, but the better way would be to find the PMF and express it as a Bernoulli or a binomial, and then derive it from there. That'll be easier.